On December 19th, interstellar object SWRI Atlas made its closest approach to Earth. To the public, it appeared to be a standard encounter. We saw a tail, we saw a coma, and we saw a trajectory that confirmed its origin from deep space. It seemed like a closed case. But in the weeks since the flyby, the narrative has shifted. While the object fades into the darkness, astronomers have been piecing together a complete dataset that contradicts the initial reports. The numbers simply aren't adding up. We now have the full picture, combining the early thermal scans taken by the Psyche spacecraft in September with the high-resolution intercepts by Mars orbiters in October. And the conclusion is disturbing, not because of what the object is doing, but because of what it is. New analysis released this week, in late January 2026, suggests that SWRI Atlas defies our standard models of density and mass. It is moving in a way that a solid object shouldn't move. Today, we're moving past the simple headlines. We are looking at an object that is seemingly too fragile to exist, yet somehow survived the journey between the stars. The question isn't who sent it, but rather, how is it holding itself together? Let's open the file. To understand why the new analysis is so significant, we have to go back to what we thought we knew just a few months ago. The story really begins in September 2025. SWRI Atlas was still inbound, plunging toward its perihelion. At that time, Earth was out of position, blinded by the solar glare. But we had an asset nearby. The NASA Psyche spacecraft, en route to the asteroid belt, had a front-row seat. Psyche wasn't designed to track comets. Its multispectral imagers are calibrated to map metallic surfaces, not the ghostly wisps of a comet. But on September 8th, its cameras captured something vital. Against the deep black of space, it resolved a faint, fuzzy halo. It confirmed that SWRI Atlas had developed a coma much further out than our models predicted. It was waking up early. Typically, water ice remains inert until it crosses the frost line, about 3 AU from the sun. But SWRI Atlas was active well beyond that range, hinting at a surface chemistry far more reactive than a standard ball of frozen water. Then came October 3rd. As SWRI Atlas crossed the orbit of Mars, the Trace Gas Orbiter and Mars Reconnaissance Orbiter were retasked to snap the intruder. The images they returned were visually stunning, but mathematically confusing. The data highlighted a profound problem with our density models. Based on how bright the object was, reflecting sunlight almost like a mirror, we expected a certain amount of mass. But the gravitational interaction and dust production were surprisingly low. The nucleus wasn't behaving like a solid, dense rock. It was behaving like something much lighter. It was shedding heat and gas in a way that suggested a highly porous internal structure. Imagine a structure similar to a fractal aggregate, like a cosmic dust bunny or ash from a campfire. It is 99% empty space, held together by faint van der Waals forces. It occupies a large volume, making it look big and bright to our telescopes, but if you were to compress it, it would have almost no substance. At the time, we thought it was just a pristine surface shedding its outer layer. But looking back at that Mars data now, we missed the most obvious clue. The object wasn't just volatile, it was incredibly fragile. Then came the closest approach to Earth on December 19, 2025. The object passed at about 1.8 astronomical units. It was completely safe, but close enough for major telescopes, Hubble, James Webb, and the Very Large Telescope in Chile, to study it in detail. Early results from ground telescopes, especially the Very Large Telescope, showed a makeup clearly different from the dry first interstellar visitor, Oumuamua. Water ice was confirmed through infrared observations, together with diatomic carbon and cyanide. These gases are known to create the bright green glow seen in many active comet Comet when sunlight excites them. James Webb Space Telescope mid-infrared observations, taken on December 15 to 16 and again on December 27th, at distances of 2.2 and 2.54 astronomical units from the Sun, produced the first mid-infrared spectra of an interstellar object, spanning wavelengths from 5 to 28 micrometers. These spectra revealed water emission, carbon dioxide emission and its hot bands, methane, the first clear detection of methane in any interstellar object, and emission from atomic nickel. Stacked images showed an extended dust coma slightly pushed away from the Sun, surrounded by a fuzzy halo stretching roughly 500 kilometers around the nucleus. Over just 12 days, the overall brightness dropped by about a factor of 4. Water production rates started high and declined rapidly. Carbon dioxide production remained elevated, and methane appeared later, likely released from deeper layers within the nucleus. Nickel is a refractory metal that normally requires very high temperatures to vaporize, so detecting it this far out is unusual. This suggests nickel exists in extremely fine, easily released grains either on the surface or within the coma. When production rates are compared with distance from the Sun, SWRI Atlas shows far more carbon dioxide relative to water than most solar system comets, along with slightly enhanced methane. This supports the idea that carbon dioxide is driving activity even beyond 6 astronomical units. Coma maps reveal that water and carbon dioxide emissions are mostly uniform, with a slight extension away from the Sun, while methane is harder to map because of its weaker signal. Radial profiles show water emissions spreading far outward due to icy grains releasing gas within the coma, whereas carbon dioxide, methane, and nickel remain concentrated closer to the dust. For several weeks following these discoveries, most astronomers concluded that SWRI Atlas was a fairly typical active interstellar comet, a primitive fragment of another star system, ejected billions of years ago and broadly consistent with current models of small body formation. However, high-precision brightness measurements from NASA's TESS satellite revealed more complicated behavior. While early estimates suggested a rotation period of roughly 15 to 16 hours, brightness variations were not consistent across different observations. These changes are driven mainly by uneven gas outing. Gas jets can produce non-gravitational acceleration, slightly altering the object's motion and orientation. Such effects are well known in solar system comets and explain the short-term brightness variations seen in SWRI Atlas, rather than rapid changes in spin. This brings us to January 2026. As SWRI Atlas moved farther from the Sun and the glare diminished, a key alignment occurred on January 22. Earth crossed very close to the object's orbital plane, with a phase angle of about 0.69 degrees, creating near-perfect opposition. This geometry produces strong forward scattering, causing dust particles to reflect light much more efficiently when viewed nearly head-on. The dust trail appears thin and sharply defined, significantly boosting brightness through an opposition surge. Hubble images captured a brighter coma, a stronger anti-sunward jet, and an extended anti-tail, clearly revealing the dust structure. The object continues to exhibit non-gravitational acceleration, caused by uneven gas release rather than sunlight pressure alone. Overall, the observations are consistent with a porous, low-density nucleus made of loosely bound ice and dust. Although material is steadily lost through gas release and dust ejection, there is no indication that the object is close to breaking apart. The story is not over. SWRI Atlas is now heading outward, crossing the asteroid belt as it leaves the inner solar system. On March 16, 2026, it will pass within about 53 million kilometers of Jupiter, well outside the Roche limit. This flyby provides another valuable opportunity for observation. Juno may collect infrared data. No significant tidal disruption is expected. The focus is on how activity changes with increasing distance from the Sun. In summary, SWRI Atlas has proven to be a remarkably informative interstellar visitor. Its composition, activity far from the sun, non-gravitational acceleration, and dust structure all refine our understanding of how comets and small bodies form and evolved in other solar systems. The upcoming Jupiter flyby adds another important chapter. Stay tuned for updates.